Okay, everybody, so we're going to learn about types of bonds today, some stuff that we've already learned about, and ease our ways into some things that we haven't learned yet. So we did recap, or we did talk about two types of bonds that occur with molecules. We have bonds that occur inside or within molecules. These are called intramolecular bonds. And there's two types of those. We have covalent and ionic bonds. If you remember, covalent bonds are bonds between atoms that are sharing electrons, and ionic bonds are bonds that occur between ions due to electrons being stolen from one atom to another. What we're going to focus on today are intermolecular forces. Now, the difference between intermolecular forces and intramolecular forces, as you can see, intermolecular forces are forces or bonds that occur between molecules. So I've got molecule A and molecule B, and there's an attraction that holds those two closer together. Whereas intramolecular bonds are just the bonds inside of the individual molecule. We'll look at some examples when we go through this. There's three types of intermolecular bonds or forces that you need to be aware of. London dispersion forces, or sometimes referred to as just LDF. Dipole-dipole, and you can see some symbols there. As I write them down on the board, you'll hopefully know what I'm talking about. And then hydrogen bonding, abbreviated as HB. Intermolecular forces, you'll sometimes see abbreviated as IMFs. Okay, so London dispersion forces is the first one that we're going to talk about. A couple of questions that oftentimes kids ask, and I feel like they're good ones to help you just keep organized. Which molecules have what, and how can I identify them, and what are these forces, and what are these attractions that I'm learning, and just to keep things straight. So first thing is, what molecules have London dispersion forces? And the answer is really simple. All molecules have them. And we could even write just elements here as well. It's really any molecule or element that have electrons. And we spent some time talking a lot about valence electrons in the bonding unit and how valence electrons pertain to making diagrams and all this kind of stuff. And we've done a lot of discussion about valence electrons. I want to make something really, really clear. The strength of London dispersion forces vary, and it varies based on the total number of electrons. So it's not just valence electrons alone that we're counting here. If you look, for example, nitrogen sits in group 5 on the periodic table, which means it's got 5 valence electrons. But its atomic number is 7, which means as an element, and in molecular compounds, it's going to have 7 electrons that it's going to contribute to the strength of London dispersion forces. So that's all you really need to know in terms of the number of electrons and the strength in which London dispersion forces varies. We'll talk more about the variance of that force when we talk about boiling points and melting points, but for now, as long as you understand that the more total number of electrons an element has or a molecule has, the stronger the London dispersion force is going to be for that molecule or element. Now, how does this occur exactly? Well, I've got an example over here that I'll run through with you guys. If you remember, electrons in these bonds here can be shared equally or unequally. Now, it depends on the electronegativity of the atoms within those molecules. In this case, carbon has an electronegativity of 2.6 and hydrogen has an electronegativity of 2.2. Now, we know the rule is that if the London dispersion force, if the electronegativity is, if the difference between those two atoms is 0.4 or less, then we know that that's a non-polar bond. And so the electrons will be shared equally. And if we look at every bond in this molecule, we know that that's the case. All of these bonds are non-polar bonds, therefore electrons are being shared equally. So it is for this molecule right here, this molecule of propane. Every bond in here is going to have electrons being shared equally. But a little piece of information to add on what we know is that we do know that electrons are moving within these orbitals. And while they may be shared equally most of the time, there may be moments in time when both electrons end up a little closer to one atom and further away from the other, just because of the random motion of electrons. And so if that happens in this molecule right here with those two electrons, and let's say that those electrons end up closer to the carbon than they do the hydrogen, what we know is that electrons are negative, and so because of that, this carbon here is going to develop a bit of a partial charge. It's going to start to develop a negative charge, and so we've been labeling that as delta negative. And this hydrogen, because those electrons have been pulled away from it, is going to become partial positive. Now, if this is occurring in this molecule too, but let's say it's occurring in this way, where the hydrogen is now getting those electrons a little bit closer to it, just by random chance, then the hydrogen is going to develop a partial negative, and the carbon is going to develop a partial positive. And so what we have here is we have now within this non-polar molecule a very temporary, and that's a key word here, very temporary dipole that forms within this molecule and within this molecule. And you can see that if two dipoles form in a similar location, then the positive nature of this dipole is going to attract with the negative nature of this dipole. And that is our London dispersion force. This little tether right here that's holding this molecule to this molecule, you can see is what's holding these two together. Now, London dispersion forces are very weak, and the reason why they're very weak is because this is all dependent on the motion of these electrons. If the electrons then decide that they're going to move back into the middle, being equally shared between those two atoms, then these dipoles are going to disappear. And if these dipoles disappear, then the London dispersion force is also going to disappear. And it is gone. Doesn't exist there anymore. And so London dispersion forces, the way that we recognize them is they kind of pop up here in this molecule in this area, and then it might pop up over here in this area. And it's just however many electrons we have kind of increases the chance at which we can develop London dispersion forces. So I like to think about it as like lottery tickets. If you go and buy one lottery ticket, your chance of winning is pretty low. If you're a molecule that doesn't have very many total electrons, then your chance of developing a London dispersion force is quite low. But if you go to the store and you buy 1,000,000 lottery tickets, your chance of winning the lottery, although it might still be kind of low, is going to be a lot higher than if someone just bought one. And so it is with these molecules as well. The more total number of electrons that they have, the better chance that they have of forming a temporary dipole somewhere within that molecule so that it can align with another temporary dipole in another molecule and create that London dispersion force or attraction between those two molecules. Okay, so the next one is dipole-dipole, and the molecules that have this are all polar molecules. And this is why being able to identify whether molecules are polar or non-polar is really important, because once we know which molecules are polar, then we also know which ones have dipole-dipole in them. And so what is a dipole-dipole exactly? So what it is it's just an attraction between one dipole in a molecule to another dipole in another molecule. And so I've got this example of hydrochloric acid here. Hydrochloric acid, we know the hydrogen has an electronegativity of 2.2 and chlorine of 3.2. And the difference between those two is greater than 0.4, which means these bonds are polar. So if I erase this stick and just draw in the electrons, we know that those electrons are being pulled closer to the chlorine and further away from the hydrogen, which inadvertently creates this partial negative and partial positive charge within each molecule. Now you can see if these guys come in close proximity to each other, again we've got this attraction between this partial negative and this partial positive. And this is the dipole-dipole that exists tethering this molecule to this molecule. Now one of the main differences between London dispersion forces and dipole-dipole forces is that this is permanent. In a London dispersion force, the attraction between dipoles is temporary because those dipoles will appear and then disappear depending on the motion of the electrons. Here, these electrons are not being shared equally and never will be because the electronegativity difference is too high. And so these dipoles that have formed here are permanent. And because these dipoles are permanent, these attractions are permanent. And so if you want to write down here this attraction is permanent, that would be a great thing to write down. Okay, so the last one that we're going to talk about is hydrogen bonding. And so which molecules have it? Only some polar molecules have hydrogen bonding. And the ones that we know have them, or the way that we can know which ones have them, is this statement right here. So anytime that we have a molecule that has hydrogen in it, and it is directly bound to a nitrogen, oxygen, or fluorine atom, then that molecule is going to have hydrogen bonding. It has to fit those stipulations though. It has to have a hydrogen atom, and it has to be directly bonded to a nitrogen, oxygen, or fluorine atom. So here's a couple of examples that I've got on the board that I'll run through with you to kind of show you what this looks like and how it happens. So water's a really good example of hydrogen bonding. What we've got here is we've got, again, these electrons in this bond right here, and we know that oxygen is very electronegative. It pulls on those electrons really strong. It's got an electronegativity of 3.4. Oxygen, again, is 2.2, quite low. And so these electrons are being very unequally shared. Now, as we've discussed before, hydrogen is unique from all the other atoms on the periodic table in that when those electrons get pulled away from it, there's no other electrons that it has in any lower energy levels. And so the positiveness or the positive nature of the nucleus is now exposed. It doesn't have electrons shielding it. And this is an interesting thing that happens, is that the lone pairs from another oxygen atom in another water molecule, if they get close enough, can form an attraction. These lone pairs are negative, they're electrons, and this nucleus contains protons, so it's positive. And so we get this attraction that occurs between those two atoms, between those two molecules. And so this is our hydrogen bond right there that tethers this molecule here to this molecule here. The same thing happens in ammonia. You can see that we've got hydrogen directly bonded to a nitrogen atom. And let's say in this one right here, those electrons, again, they're all being pulled really close to the nitrogen, but this one shows that it's being pulled really close. That exposes the positive nucleus of that hydrogen atom, and these lone pairs on this nitrogen, which are negative, are then going to be attracted to the positive nucleus in the other hydrogen atom. And that's your hydrogen bond, tethering this molecule to this one. Now, a couple of mistakes that kids make, and so I want to point these out. First one is that lots of times kids just kind of stop there. They're like, oh, hydrogen bonding has hydrogens in it. So if it's got hydrogens in it, it has hydrogen bonding. And that's not the case. Remember that it has to have hydrogen directly bonded to a nitrogen, oxygen, or a fluorine atom. And so if you look at this one, methane, CH4, it doesn't have a hydrogen directly bonded to one of these three atoms, nitrogen, oxygen, or fluorine. And so because of that, it doesn't have hydrogen bonding. Another one that kids will often make a mistake at is they'll see a molecule like that that's got a fluorine in it. And so, hey, it's got nitrogen, or it's got hydrogen and it's got fluorine in it. That's got to have hydrogen bonding. But again, this doesn't fit this definition here where it's got to be directly bonded or directly bound to the fluorine atom here. It's not directly bonded to it. The hydrogens are all directly bonded to the carbon. And so because it's not one of these three, again, it doesn't fit that description of a hydrogen bond, and therefore that molecule will not exhibit hydrogen bonding. Now that we've talked about all three of these, what we can do is we can compare the strength of these three. So if I'm looking at the strength of IMFs, and I were to rank these in order from strongest to weakest, I would rank them number one, hydrogen bonding. And the reason why is because I've got things that are fully negative interacting with things that are fully positive. And so that's the strongest out of the three. The second is dipole-dipole, and it's because it's an interaction between partial charges that's permanent. And then the last one that's the weakest is London dispersion forces. And that's the weakest because it's like a dipole-dipole, it's an attraction between temporary or partial charges, partial negatives, partial positives. But that attraction is only temporary, unlike the dipole-dipole force that's permanent. So that's it for intermolecular forces. Hope you guys enjoyed the video, and we'll see you in the next one.